not 100% pure nitrogen, right? So how do you put that, how does that change the flammability diagram, and how you would put that on there? Because you're likely not going to have access to 99.999% pure nitrogen. You might have 2 to 5% oxygen in that nitrogen, which means that you already have a little bit of oxygen in there. So when you determine, right, which means you're going to have to reduce the fuel concentration a little bit below what you would, right, if you were using pure nitrogen, because there's already a little bit of oxygen in there. So chapter 7 is dealing with preventing fires and explosions, and we've already done some of this, right? We just talked about the out of service fuel concentration. So the way you do that, you draw your flammability diagram. This is obviously the one for methanol that we just drew. And then you connect the pure air point with the corner of your flammability diagram. Draw a straight line and read where it hits the fuel axis. So in this case, our out of service fuel concentration for methanol would be 14%. You can also, if you want, calculate the out of service fuel concentration, and you can, they have, in one of the appendices is deriving where these equations came from. It's just the level rule, basically. But you can use either the LFL or the LOC concentration, right, to that. But you do need to determine the stoichiometric coefficient for that. Those equations are given in the book. But I want you to know how to do it graphically as well. So, right, one way to see if your graphic right method was approximately okay would be to calculate one, right? And just double check. So now let's say we have methanol may not be the best one. Let's say we wanna actually introduce a flammable gas. So we're not putting in a liquid, we're putting in a flammable gas. So we're down here at 100% air, and we wanna go up to 100% fuel. Okay, so if we take this container and we start filling it with fuel, we're going to go on this line, right, if we don't do anything. And as you know, you will go straight through the flammability zone if you do that. So what you want to do is from here, you want to bring down your oxygen concentration until you're at a safe concentration. And again, obviously what you could do is bring it all the way below the limiting oxygen concentration. But if you can get away with a little bit less, that's what your company's going to want you to do, because it's going to be cheaper, right? You can use less pure nitrogen. So you go from that point, and that's where your starting point. And in this case, to determine the in-service fuel concentration, in-service oxygen concentration. Sorry. Here, the arrow up here. You go from 100% fuel and connect a line with the corner of your flammability diagram again, and read your oxygen concentration down here. So you draw a straight line from 100% fuel through this corner point, and then you read the in-service oxygen concentration. And as you can see in this case, we're pretty much right on the limiting oxygen concentration. But sometimes that in-service oxygen concentration is a little bit higher than your limiting oxygen concentration, but you're still safe because you're avoiding this corner, right? This nose here of your flammability. So my plan for the second hour was to go over a little bit more in chapter 7 and look at purging. So if we're doing things like that, bringing vessels into to service, or taking vessels out of service, we need to know, for example, how many times do we need to purge the system, right? We can do pressure purging or vacuum purging. And the reason for me, instead of so switching the problem solving session, or do a little bit of problem solving and adding that, is so that I don't go over everything too close to the exam. I want to try to cover it before, right, with a little bit of time for you to sort of process it, I guess. So do you, before I start doing that, would you like a little break?
Yes.
A little break?
Yes.
Short break to end early.